Okay, so we're going to talk about, this is the last little portion of the stereoisomers chapter. So we're going to talk about kind of some other stereoisomeric relationships that you guys need to be aware of. And then at the end, we're going to talk about a couple different ways that we can imagine stereoisomers, different type of projections that we can use to easily visualize whether or not something is an enantiomer versus maybe other types of stereoisomers. Okay, so now I'm going to go back to this little chart just to remind you about what we're talking about. So when we're dealing with isomers, again, isomers tell us that something has the same molecular formula. So this, anytime anything is an isomer, we have the same exact molecular formula. And we talked about, okay, well, we've already talked about constitutional isomers. Again, constitutional isomers have the same molecular formula because they're isomers, but they have different connectivity of atoms, right? So this is comparing something like propanol to, well, now I can't think of an easy stereoisomer. So something like butanol to something like propanol, right? So again, we have 1, 2, 3, 4, it's the same exact molecular formula. We have different connectivity of atoms. So these guys would be constitutional isomers, okay? Now, in this chapter, we're not dealing with constitutional isomers. We're dealing with stereoisomers. And so again, we have same molecular formula because they're isomers. But now when they talk about being stereo, they have this same connectivity of atoms, okay? Now, we've been calling these things, if they're stereoisomers, non-superimposable, because if they were superimposable, it'd be the same exact compound. So that wouldn't be dealing with any type of isomeric relationship, okay? All right, so now we have specifically talked about enantiomers, right? So now enantiomers are stereoisomers. They have same molecular formula, they have same connectivity of atoms, and they are mirror images of one another. And that's the big definition with respect to enantiomers. So these guys were non-superimposable mirror images, okay? And a nice easy example of an enantiomer would be something like this, right? So if we had a molecule here, we have a chirality center at this carbon, it's sp3 hybridized. There are 4 different groups around it. The enantiomer of this would be its non-superimposable mirror image, and we can draw that by just changing the orientation about that chirality center, right? So chlorine was on the wedge, or the dash, we can now put it on the wedge, and we have drawn its enantiomer, right? And again, you can imagine this molecule in a mirror, and you can draw it that way, or you can just switch the wedge and dash on the chirality center, okay? Again, non-superimposable mirror images, okay? Now, there is another type of stereoisomer that we haven't talked about, and these are what are called diastereomers. So I'm going to spell that out, or phonetically spell it out. So this is dia, so diastereomer. So diastereomer, okay? So now, what is a diastereomer? So diastereomer is a non-superimposable, non-mirror image. Okay, so enantiomers were mirror images. Now there's going to be things that have same connectivity of atoms, same molecular formula, but now they're not going to be mirror images of one another, and they're also not going to be superimposable. Okay. Now, a really good example of what a diastereomer is comes in the form of that cis-trans stereoisomerism that we talked about at the beginning of the chapter. So remember, if we have an alkene has a carbon-carbon double bond. And remember about that double bond, we are not allowed free rotation, so we cannot freely rotate this. No free rotation. So because of that, whatever groups, because it's trigonal planar, whatever groups are attached to that carbon are stuck in their position. They cannot rotate with respect to one another, right? So if we look at this molecule, we say, okay, this is carbon 1, this is carbon 2. We've got a methyl group attached to carbon 1 and a hydrogen. We've got a methyl group attached to carbon 2 and a hydrogen. And for this stereoisomer, we would have called this the cis version of the stereoisomer because the 2 methyl groups are on the same side of the double bond. So this is our cis stereoisomer, cis alkene. Okay, now if we compare this guy to this guy, we have the exact same, again, connectivity of atoms, the exact same molecular formula, right? We have carbon 1, we have carbon 2, right? We've got a methyl group attached to carbon 1, a hydrogen attached to carbon 1, a methyl group attached to carbon 2, a hydrogen attached to carbon 2. Okay, so again, we have same connectivity of atoms, we have same molecular formula. Okay, these guys are non-superimposable, right? So again, if I tried to superimposable, if I tried to pick this guy up and overlay it onto this guy, I would not get the same thing, right? They're non-superimposable. And now if I tried to imagine a mirror here, and I tried to reflect this guy through this mirror, I would not get this compound, right? This is not the mirror image of this, okay? And so this, because of that, this cis-trans stereoisomerism, this is an example of two diastereomers. Right, these are diastereomers with respect to one another. They are non-superimposable, non-mirror images, okay? And again, this guy was cis. We would call this one trans because these guys are on opposite sides with respect to one another. So opposite is trans, okay? All right, so again, what's the difference between enantiomers and diastereomers, right? Both of them are non-superimposable. Enantiomers are mirror images of one another. Diastereomers are non-superimposable, non-mirror images of one another, okay? Okay, so where are we going to see these diastereomers at with respect to our alkanes, which is what we've been dealing with, our sp3 hybridized carbon centers? So now let's imagine we have a molecule like this, right? And if we look at this molecule, now we're not dealing with cis-trans stereoisomers, but we do notice that there are going to be actually two chirality centers in this molecule. So remember, a chirality center is sp3 hybridized carbon that has 4 unique groups around it, right? So here, if we look at this first carbon, we have an OH group as 1. We have this way around the ring, which is different than this way around the ring. And then we do have an implied hydrogen right here, right? So this guy is a chirality center. If we then move down to this guy, we'll also note that, again, this is a chirality center. We have a methyl group here. So we have a CH3 group here. We have this way around the ring, which is different than this way around the ring. And again, we have a hydrogen that is implied. So those are 4 unique groups around that sp3 hybridized carbon. This is also a chirality center, okay? All right, so now, if we imagine, because we have 2 distinct chirality centers, so 2 chirality centers, we're now going to imagine all of the possible stereoisomers that can emerge from 2 chirality centers, okay? So first thing I'm going to do is I'm going to redraw this guy. I'm going to try to be not messy, but it's ugly, obviously. And then I'm just going to start by taking the OH for this carbon. And let's say we start by putting this guy on the wedge, right? So one way that we can arrange these guys is to have that OH come out at us. Therefore, the hydrogen would be on the dash. It would be implied going in. And let's also put the methyl group on the wedge as well. So let's imagine that methyl group, and we'll go ahead and draw the CH3 is coming out at us. And then therefore the hydrogen that's implied is going to be on the dash, okay? So this is one of these ways, one of the ways that we can arrange these atoms, right, to produce a stereoisomer of this compound, okay? Now, if this is the way that we've done this guy, and I wanted to draw its enantiomer, so it's non-superimposable mirror image, enantiomer, all I'm going to do is I'm going to take what was on the wedge and I'm going to put it on the dash, right? So I can go ahead and just redraw this guy. I'm going to now exclude the hydrogens because they're just going to get in my way. The OH was on the wedge. If I want to draw the enantiomer of that compound, I'm now just going to put it on the dash. I'm going to do the exact same thing for the methyl, right? So the methyl was on the wedge. It's now going to go to the dash. And that is a quick, easy way to take something and draw the enantiomer of it. Just switch the wedge in the dash, okay? And again, if you want to imagine a mirror, you can imagine a mirror behind it or a mirror in front of it, and you would get essentially this compound, okay? Okay, so that is its enantiomer, right? But there are other ways that we can arrange the OH and the CH to draw different stereoisomers for this compound, right? So if I redraw my cyclohexane, right, and now let's say for this guy, I'm again going to start with the OH on the wedge. But now for a different molecule, right, a unique molecule, I'm going to put the methyl group on the dash, right? That is a different way that I can arrange these atoms to produce a different stereoisomer, okay? Now again, if I want to draw the enantiomer of this guy, all I have to do is switch the wedge and the dashes, right? So if the enantiomer of this, the OH would now be on the dash, and the methyl group would be on the wedge, right? So these guys are, again, enantiomers of one another, okay? All right, so now, for every molecule, it has a mirror image, right? A non-superimposable mirror image. It has an enantiomer sometimes. And I'll mention that there is an exclusion to this later on, but right now, if you have a molecule, it has an enantiomer, okay? But now, if these guys are enantiomers to one another, then the question is, well, what are these guys and these guys with respect to one another, right? Again, they have the same connectivity of atoms, right? They have an OH, an H, a CH3, and an H. But they're non-superimposable, and they're also not mirror images anymore, right? So this guy and this guy, we'll call this guy 1 and this guy 3. These guys are non-superimposable, non-mirror images. These guys are diastereomers. Stereoisomers. Same thing for, let's call this guy 2 and this guy 4. 2 and 4, these guys are also non-superimposable. Same connectivity of atoms. They are non-mirror images of one another. These guys are also diastereomers. And then if we look at something like 1 to 4, these guys are also diastereomers. They're non-superimposable, non-mirror images. And then 2 to 3, these guys are also diastereomers. They're non-superimposable, non-mirror images. Okay, so we had a molecule. It had 2 chirality centers, right? Overall, for the total possible stereoisomers that it could give us, this ended up being 4. We could arrange those atoms or those groups around those chirality centers in 4 different distinguished ways. For each molecule, for each stereoisomer, it gave us 1 enantiomer, and then it gave us 2 diastereomers to itself, right? So, for example, molecule 1 has 1 enantiomer, and then it has 3 and 4 as its 2 other diastereomers. Okay, so again, 2 chirality centers is going to give us 4 different stereoisomers. What happens if we have 3 chirality centers, right? So, for example, let's say we had a molecule like this. And again, we're going to have the OH here. We're going to have a methyl group here. And now we're going to put a chlorine on this carbon. So this is not giving us any spatial arrangement. We're not looking at different stereoisomers here. But again, these are 3 different chirality centers. So now we have 3 chirality centers. And lucky for us, the book already went through and drew all of the different possible ways that we could arrange those groups to get different stereoisomers, right? For the first way, we can put everybody on the wedge. Again, the enantiomer of this guy is just going to be everyone on the dash. So again, these guys are enantiomers. We could have 2 on the wedge, 1 on the dash. To draw the enantiomer, we're just going to switch the wedge and the dashes. We could go through these different permutations. So we have the OH on the wedge, the chlorine on the wedge, the methyl on the dash. Again, if I want to draw the enantiomers, I'm just going to switch those guys. And then finally, we have the OH on the wedge, these guys on the dash. Again, to switch them, we're just going to draw the enantiomers of that, okay? So these are all of the possible stereoisomers if we have a molecule with 3 chirality centers. If we go ahead and count them, we have 1, 2, 3, 4, 5, 6, 7, 8. So when we had 2, that gave us 4. Now that we have 3, we're going to find 8. And then this is going to go on and on and on. If it was 1, there was a 2. If there was 4, that's going to give us 16. So long term, dependent on the number of chirality centers, we're going to end up with 2 to the n stereoisomers, right? Where n is the number of possible chirality centers in the actual molecule. And this is giving us the number of possible stereoisomers. Okay, so again, we have enantiomers of one another. But again, the relationship between this guy and this guy, and this guy and this guy, and this guy and this guy, these guys are all diastereomers. They are non-superimposable, non-mirror images. Okay, so if we have a molecule with 3 different stereoisomers, then each molecule is going to have an enantiomer, 1 enantiomer, and then it's going to have 1, 2, 3, 4, 5, 6 different diastereomers possible in theory. Okay. Okay, so just to kind of rehash that, the number of stereoisomers depends on the number of chirality centers that are present in the molecule, right? So, and I do want to state this specifically, the number of possible stereoisomers, that is the maximum number. Sometimes we're actually going to have less than that, and I am going to talk about in a second when you're actually going to see the less than the maximum number of possible stereoisomers. But again, this depends on the number of chirality centers in the molecule, right? So if there were 4 chirality centers in the molecule, then that would give us 2 raised to the 4th power, which is 16. So a lot of times with respect to these types of problems or the things that you're going to be asked, they're going to have you identify the number of chirality centers, and then they're going to want to know the maximum number of possible stereoisomers. So for example, they're going to give you some nice hard molecule like this, cholesterol. So cholesterol, if we go through and we look for the number of chirality centers, we're going to find 1, 2, 3, 4, 5, 6, 7, 8. And again, we're looking for sp3 hybridized carbon that has 4 unique groups around it, right? So for cholesterol, that ends up being 8 different carbons. So the possible number of stereoisomers is going to be 2 raised to the 8th power, which ends up being 256 possible stereoisomers, right? So it's 256 possible, maximum number of possible stereoisomers. And this is kind of a nice illustration of why nature or biology or whatever you want to think of is kind of unique in the fact that there are 256 different ways that you could make this molecule, and nature is very stereospecific, meaning that it only makes one, and it makes a very specific stereoisomer, even though, again, there are 256 possible stereoisomers that you could get out of this molecule. Okay, so I'm going to go ahead and give you guys a problem, all right? So what I've done here is I've given you 2 sets of molecules, right? So I've said I want to know the relationship between this molecule and this molecule, and I want to know the relationship between this molecule and this molecule, right? And I'm asking you whether or not these guys are enantiomers with respect to one another, or whether they are diastereomers, right? So remember, enantiomers are non-superimposable mirror images, right? And diastereomers are non-superimposable non-mirror images, okay? So go ahead, try both of these. Go ahead and pause the video and then come back for the answer. Okay, so for the first one, this is kind of easy the way that they've arranged this for us, at least for me to see it. So they've essentially drawn the molecule the exact same way, right? So let's say that we took this guy, right? And I wanted to imagine this guy, and I actually wanted to go ahead and draw out the enantiomer of this, right? So remember that if we want to draw the enantiomer, a nice, quick, easy way to do it is to take everything that's on the wedge and turn it into the dash, and everything that's on the dash and turn it into the wedge, right? And so if I wanted to draw the enantiomer of this guy, I would take the OH group, right? This is what a chirality center, and that is on the wedge, so now, or that is on the dash, so in the enantiomer of it, I'm going to go ahead and draw it on the wedge. And then another chirality center is here. If I want to highlight, this is a chirality center. It is on the dash in our original molecule, so to make the enantiomer, we're just going to draw it on the wedge. And then it goes down, that's ugly, and I'm going to just erase it. And then it goes down to this guy down here that has an OH that's on the wedge. So again, to draw the enantiomer of this, I'm going to put that OH on the dash. Right, and so then we end up with the enantiomer of that original molecule, right? If we go over here, we find that, okay, our OH is on the wedge, that looks good. Our little methyl substituent, or this meth-propyl substituent that's coming off, is on the wedge, that's good. But now the only problem is this OH, right? If it was the enantiomer, it would be on the dash. It is on the wedge in this molecule. So these guys, these two, are not enantiomers. They still have the same connectivity of atoms, though, right? They're just non-superimposable and they're non-mirror images, right? So these guys are going to be diastereomers. And that's a nice, easy way to figure that out, is to look at one of them and say, okay, what would the enantiomer actually look like? Is that the same exact image that I am presented with in the second molecule? In this case, it wasn't, so they have to be diastereomers. Okay, so we're going to go down to the bottom one here. Now, the problem with this one is that they've kind of switched our orientation. That can kind of be a hassle to visualize correctly, right? So, for example, this is the same connectivity of atoms. So if you were wondering about that, a nice easy way to check this would be 1, 2, 3, 4, 5, 6, 7, 8 carbons. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons, right? So it's the same parent chain. Here we have a methyl group on carbon 3 and a methyl group on carbon 4. Here we have a methyl group at carbon 3, and here we have a methyl group at carbon 4, right? So this methyl, this methyl, this methyl, this methyl, okay? So these guys are going to be stereoisomers. They have the same connectivity of atoms. The question is, are they mirror images, or are they non-mirror images, okay? Or are they, well, that's not even an option, so forget that, okay? Now, again, they've rotated this, right? They've put the methyl group on the dashed line here, and they put this guy on the wedge, and that's not what we saw, or it's not the same orientation over here, okay? So now, the way that you would go about, at least the way that I would go about answering this, is instead of trying to say, okay, well, this guy's going to be on the wedge, and it's going to be on the dash, I would actually just go ahead and assign absolute configuration to both of these chirality centers, right? So when I mean absolute configuration, I'm talking about R versus S, right? If, let's say, we had an S and an R in this molecule on the left, the enantiomer of this would actually have an R versus an S, right? So you're just going to see switching of that absolute configuration with respect to the enantiomers, okay? So that's how I'm going to go about answering this question. I'm going to focus first on this carbon, carbon 3, and again, I'm just going to draw out the two lines and then the dash and the wedge. And I'm going to go ahead and assign priorities, right? So this would be 1, 2, on the dash would be 3, and then that implied hydrogen is on the wedge, that's 4. Again, to assign priority, or to determine rotation, I have to put 4 on the dash. I'm going to switch it with 3. If I switch these guys, then I also have to switch these guys, so this is 2 and 1. So 1 to 2 to 3, this is counterclockwise. So this guy is S. Now I'm going to do the same thing for carbon 4. So I don't like that. We've got dash. We've got a 1, a 2, a 3. Again, 4 is implied. So I'm going to switch 3 and 4. So we've got 3. We've got 4, but then if I switch 3 and 4, I have to switch 1 and 2. So now we have 2 and 1. So 1 to 2 to 3 is counter again. So this is also S. So we have S and S over in the original molecule. If this ends up being R and R over here, then they're enantiomers. If instead it ends up being S and R or any other permutation of that, then they would be diastereomers, okay? So I'm going to go ahead and start with 3. Here we've got a 1, a 2, a 3. Hydrogen's already implied on the dash. So we go from 1 to 2 to 3. This is clockwise. So this is R. And then for this guy, we'll go over here. We've got 1, 2, 3. 4 is here, so I'm going to switch those two. So I'm going to switch 4 and 2. So this ends up being 4, this ends up being 2, but then I have to switch 3 and 1, so this ends up being 1, this ends up being 3. So 1 to 2 to 3 to 1, this is also clockwise, so this is also R. So S and S to R, these guys are enantiomers. You see a complete inverse in terms of the R and S relationship. If that occurs, then that's the enantiomer of the other molecule. Again, if this guy had been S and S, and you had gotten R and then S, or S and R, then these guys, then that relationship would have told you that they're diastereomers. But because the S turned into an R, the S turned into an R, the S turned into an R. This is the mirror image of this molecule. These guys are enantiomers. Now we're going to go into this concept of what happens when we don't actually get the exact same number of max stereoisomers that we have predicted. Okay, so we're going to utilize our cyclohexane as an example in this. And this is going to be a di-substituted cyclohexane, so we're going to have a methyl group on one carbon and a methyl group on another carbon. Okay, so this is what we're starting at. How many chirality centers do we have in this molecule that we have drawn? We have 2, okay, so we can go in and say we've got 1 here, we've got 2. So for max number of possible stereoisomers, this should be 2 raised to the what power? 2. So max number, we should get 4. 4 possible stereoisomers, okay? Okay, so now we're going to go through and we're going to figure out, do we actually get that max number of stereoisomers, okay? So if we take this guy and we arrange it, right? So let's say that we're going to start with this guy being on the dash and this guy being on the wedge. Our 2 methyl groups, what are they relative to one another in this guy?
Trans.
They're trans, right? So this would be 1 pointing up, 1 pointing down. How would I draw the enantiomer of this one?
Switch the dash to the
Right, so I could draw this again. I need to copy paste, makes it easier. I can switch the dash and the wedge, okay? Are these 2 distinct compounds? So if I pick this up and if I rotate it and I put it down, do I get the same exact thing?
Yes.
No, because they're non-superimposable, right? Enantiomers are non-superimposable mirror images. If I pick this up and I rotate it, I'm not going to get the same compound. Because again, if I did that, pick it up, rotate it, what was on the wedge would go to the dash up here, which doesn't match up. Okay, so good, we have 2 enantiomers. Now, what is the other way that I could draw this and trying to figure out the other stereoisomer? So the first one, I put this guy on the wedge, this guy on the dash, and I drew the enantiomer. What is the other possible permutation for a different stereoisomer?
2 dashes.
Right, so I could put both of these guys on the dash, or a wedge, we'll say. Right, so now, how would I draw the enantiomer of this? So I've got both of these guys on the wedge. How would I draw the enantiomer?
Okay.
I draw dashes. Now the question is, are these distinctly different compounds? So if I pick this up and I rotate it and I plop it down here, what was on the dash, where is it going to go? On the wedge, right? So are these different compounds?
Yeah.
If they are superimposable, then they are not different. They are the same exact compound, okay? These guys were non-superimposable. These are 2 distinctly different compounds. But when I take this guy, I pick it up and I superimpose it, I get the exact same thing, okay? So do I get 2 different molecules here? No, okay? So because of this, this version is what we call achiral, meaning it's not chiral, right? Even though it has chirality centers in it, it isn't actually chiral. It doesn't have a handedness. There is not a non-superimposable mirror image. Because again, when we draw the mirror image, it is superimposable. It's the same compound. Okay, so we don't get an enantiomer for this guy making this guy achiral. Okay? Now, for this situation where we had 2 chirality centers, we were supposed to have a maximum of 4 stereoisomers. How many do we actually get for this? We get 1, 2, these are distinct, and then 3, right? So for this guy, there are actually only 3 stereoisomers present. Okay, so now this is always going to be a possibility where we get less than the maximum number of stereoisomers if we have molecules that have even numbers of chirality centers, right? We have 2 chirality centers in this molecule. That's an even number. So this possibility that we're going to have less than the maximum number is there. Now the question is, how do we know, right? Besides having to draw everything out and be like, oh, wait a minute, this enantiomer is the same exact thing, so it can't be an actual stereoisomer. So to talk about that, we're going to introduce 2 concepts, or 2 different types of what we call symmetry operations, okay? Okay, so the first type of symmetry operation that we're going to introduce is something called rotational symmetry, okay? So rotational symmetry we're going to kind of introduce via our little trans isomer here. So remember that the trans isomer, it did have an enantiomer, right? It did have a non-superimposable mirror image, okay? Okay, so now what we're going to do to this trans isomer is we're going to take a skewer and we're going to just impale this thing right down the middle, okay? So what I mean by impaling it, I'm literally going through this like this, okay? I want you to look at the molecule as it is right now, and I want you to close your eyes, okay? I want you to rotate this 180 degrees, and then I want you to open your eyes again. Can you tell that anything happened? So again, if we skewer this right down the middle, we rotate it 180 degrees, you get the exact same molecule back. Yes, right? So because of this guy, our trans isomer, possesses what we call rotational symmetry. And this guy, this 180 degrees rotation, this axis here, this is what we call an axis of symmetry. So if you have rotational symmetry, you have an axis of symmetry, okay? And that axis, again, is that thing that you can rotate 180 degrees and get back to the exact same molecule that you were originally. Now, let's compare that with our cis version of this guy, okay? So now, in our cis version, if we go in and we skewer this, right? We skewer it and we rotate it 180 degrees, can we tell that we did that? Do we get the exact same molecule back? So again, if I'm skewering this guy right down the middle and I rotate it 180 degrees, where do those methyl groups go? They're not on top anymore. Yeah. They're on bottom, right? So if I do that, can I tell that I did that? Yes. Yes, I can. This guy, I couldn't. This methyl group, when I rotate it 180, goes up. That methyl group goes down. I couldn't tell the difference, right? This guy, though, skewer it, rotate it 180, those methyl groups are now down. And so I can tell that I did something, okay? So because of this guy does not have an axis of symmetry, right? It does not contain or possess rotational symmetry. Now, if it doesn't have an axis, what does it have? Okay, so now let's imagine that we take this molecule and we put a mirror right down the middle of it. Okay, so we slice this guy in half, we put a mirror right down the middle, and now let's have the left-hand side reflect to the right-hand side and vice versa. Okay, so again, close our eyes, we look at it, we close our eyes, we have those sides reflect, we open them, do we get the same molecule? Does the left-hand side directly reflect over here to the right-hand side? Yes, right? So because of that, this guy has what is called reflectional symmetry. And we have, instead of an axis of symmetry, we have a plane of symmetry. Okay? Okay, so what's the purpose of this? What are we doing this for? Yeah. Who had an enantiomer, the trans or the cis? Trans had the enantiomer, right? So we could predict that, oh, that guy had an enantiomer, good, those are two stereoisomers. Who was achiral? Cis, right? So rotational symmetry isn't going to tell us anything about being achiral, right? Instead, if you have a plane of symmetry, if you have this reflectional symmetry, then you will be achiral. If you can divide that molecule in half and reflect one side to the other, that means that it's not going to have an enantiomer. It's not going to have a non-superimposable mirror image. It is an achiral molecule, right? And that's what we saw when we looked at our cis enantiomer or our cis stereoisomer. That guy didn't have one. When we drew it, it got the same molecule back. If you have a plane of symmetry, you're always going to be achiral. So how do you know when you're drawing out all of these various stereoisomers? You're looking for a plane of symmetry. If a molecule has a plane of symmetry, it will be achiral. Okay?
And then the rotational symmetry?
Nothing. A lot of people confuse rotational and reflectional, and I think we just introduced rotational to show you we have an axis. An axis of symmetry doesn't have anything to do with any of this. It's the plane of symmetry that we're looking for in determining whether something or not is achiral. Okay, so one more little vocabulary word. This guy, that was our cis molecule, right? That was achiral because it had a plane of symmetry. We call compounds meso compounds, okay? So they're going to be these compounds that don't have an enantiomer because they have this plane of symmetry, because they're achiral. And if you do possess a meso compound, then you're always going to have less than the maximum number of stereoisomers. Also, meso compounds are not optically active, meaning if you put them in a polarimeter, they don't rotate plane polarized light like chiral molecules do because they don't have any chirality to them, even though they have chirality centers.
So they don't have R's and S's?
They don't have R's and S's, no. There's no, even though they're chirality centers, they are not chiral themselves. Well, they do have R and S, but it doesn't matter. The R and S is the same for both of them, right? You see what I mean?
So cancel each other out?
Yeah, they cancel each other out. So this guy rotates, but then this guy rotates the other way, so. Okay, so now, again, to kind of reiterate this, now we introduce this possibility that even though we can now calculate the maximum number of stereoisomers possible, given the number of chirality centers, some molecules will not have that max number, right? So a lot of times what I'll give you is a molecule, and I'll say, draw out all of the possible stereoisomers for this molecule. If I do that, it's probably a trick in the fact that this probably does possess a plane of symmetry in one of the stereoisomers, so you probably will have a meso compound at some point in time. Okay, so let's go ahead, let's try this one, and let's try this one. And in this question, I want you to draw out all of the stereoisomers for these two compounds. Okay, and so what I indicated on the board is we actually only went through drawing out the stereoisomers for this one and this one because I had already really done this. This was my example. Okay, so again, if we look at these two molecules, so we'll start with A, the first one. We'll note, first off, the chirality centers that are present in these molecules, right? So again, we're looking for carbon with 4 unique groups attached to it. We find that we have a chirality center here and a chirality center here, right? And so now we can kind of go through and draw out the different permutations. So let me redraw the cyclopentane. It's an ugly one. I think the worst is cyclopentane. For whatever reason, I've never been very good at drawing it. Okay, so we're going to start here, and we're going to go through the different permutations of how we can arrange these other groups about these two chirality centers to get these various stereoisomers, okay? So in the first one I'm going to do, I'm going to take, let's say, this methyl group, and I'm going to put it on the wedge on this side. So we'll say wedge here. And then on the other side, let's say I'm going to put it on the dash, right? So the other guy, instead of putting it on the wedge, I'm going to put it on the dash, right? So now let me just copy paste this, even though it's ugly. It probably shouldn't be copy pasted. So now, if I want to draw the enantiomer of this, I can. Super easy. So if I want to draw the enantiomer of the original molecule I drew, all I have to do is change my wedges and my dashes, right? So for the enantiomer, what was on the wedge is now going to be on the dash, and vice versa. So the other guy was on the dash, now it's going to be on the wedge, okay? Okay, so let me rotate this. That is ugly. Okay, so we draw one, we draw the enantiomer, right? So notice that for this molecule, for meso compounds, what we're looking at is a plane of symmetry, right? And if I had drawn a plane right through the middle of this compound, or a mirror plane right through the middle of this compound, this guy, which was up here, would not have been reflected over here, right? On the other side, we have it going down, right? So there is no plane, there's no mirror reflection here, right? So we do not possess a plane of symmetry. So therefore, we don't have a meso compound, right? This does have an axis of symmetry, right? So if we had skewered this right down the middle and we had rotated it 180 degrees, we would get the same compound, right? But again, an axis of symmetry has nothing to do with whether or not we have the presence of a meso compound, right? So there is a distinct enantiomer. This guy is not superimposable upon this guy, okay? Now, because there are two chirality centers, right, there's supposed to be 2 n, so 2 raised to the 2 number of stereoisomers, so 4 maximum possible stereoisomers. When we go through the other permutation of drawing these guys, so let me go ahead and copy paste this one. Now I'll just redraw it. So the other version, or the other stereoisomers of these guys is this, and then I'll copy paste this guy and draw that down here, right? So I could have also had said, okay, well then I'm going to put all of these, both of these methyl groups on the wedge, right? And then I say, oh, well, and it's an enantiomer, I'm going to put them both on the dash, right? So for this guy, I draw both on the wedge, and then for the enantiomer, they're both on the dash, right? Now, hopefully you guys will see and you'll recognize the fact that actually both of these are the same molecule, right? So these guys are the same molecule. And that means that this molecule does not have an enantiomer, even though it has chirality centers, right? When we draw its enantiomer, and when we draw its mirror image, we get the same exact thing, right? So this is what we would call a meso compound. And again, ideally, you would have been able to notice that early on, because now this guy does possess a plane of symmetry, right? If we draw a mirror right down the middle of it, this side is directly reflected over here, right? So we have a plane of symmetry that indicates that there's going to be at least the presence, or that usually any molecule that has a plane of symmetry is a meso compound and will not have an enantiomer. Okay, so because of that, when we draw this, we don't have this guy. There is no enantiomer for this. And if you drew the enantiomer, you would be wrong. Right? This is a meso compound. So for this molecule, there are only 3 possible stereoisomers. There is this guy with its enantiomer, and then this guy. These guys comparatively are what we would again call diastereomers. Diastereomers. These are non-superimposable, non-mirror images. Okay, so then we'll move on to B here. Again, we're going to take this, we're going to draw out all the possible stereoisomers. So I've got 2 chirality centers. I'm going to go ahead, so if we have 2 chirality centers, 2 raised to the 2 is 4 maximum possible stereoisomers. I'm going to go ahead and draw the OHs on the wedge and the dashes for this molecule. Right, so one way that we can arrange these guys is we could say that we've got an OH here. This guy is going to also be here. Now to draw the enantiomer of that, I'm just going to switch what is on the wedge with the dash. So we have an OH here and an OH here. Another way that I could arrange these is I could put this OH on the wedge and this OH on the dash. And then another way that I could arrange these is I could put, or draw the enantiomer of it, where I switch the wedge and the dashes, and we're here. Okay, so again, these guys are enantiomers of one another. These guys are enantiomers of one another. But now, if we look at this guy and this guy, there is a plane of symmetry in here. If we pick this one up and we rotate it, right? If I rotate this way, meaning like I pick it up like a pancake and I'm going to flop it back down like a pancake, these things that were going into the board, right, would now be popping out at us. It would essentially be this exact same molecule, right? Because there's a plane of symmetry here, this guy and this guy are the same molecule, right? So this is a meso compound, meaning that there's only one way that we can draw this, okay? So we do get this compound, or you could draw it like this. It doesn't matter which way you draw it. Because of that plane of symmetry, though, there is no enantiomer for that guy. But these guys are different. They are enantiomers of one another. So overall, we have 1, 2, 3 possible actual stereoisomers, where there could have been 4 maximum, right? So these guys are 3 stereoisomers, we don't get the 4 maximum number because, again, one of these was a meso compound. So what are Fischer projections, right? So notice we use that word projection a lot. Where have we seen projection before? Newman was one, right? Why did we draw Newman projections besides just annoying you? What were we looking for?
To see how they rotate,
Where their groups are relative, right? Highest and lowest energy. What other projections have we kind of looked at? We maybe didn't draw. There was a sawhorse. There was a chair, right? So again, why are we doing those things? Why are we trying to draw those things? In theory, they're supposed to make your life easier, right? So that's the entire purpose of these projections, is whatever we're looking at, if we draw it this way, it's going to be easier to see various things, okay? So it's the exact same thing with the Fischer projection, except now with the Fischer projection, what we're using this for is to be able to see chirality centers and whether or not things are enatiomers versus diastereomers much easier compared to if we had to draw it in bond line the entire time, okay? So now why would this ever come about? So this was originally invented by a guy named Emil Fischer, who was a German biochemist. He was dealing with sugars, right? And he investigated a lot of sugars, and sugars have a large amount of chirality centers. I was about to say shit ton, but that's not something that I should say, especially on recording. Right, so there are lots and lots and lots of different types of sugars, okay? And they all tend to have a significant amount of chirality centers in them. So for example, if we look at this guy, we've got a 1, 2, 3, 4 carbon sugar. How many chirality centers are present in this molecule?
2.
There are 2, right? So in the middle here, we've got 1, 2. It's easy to see when we draw it like this, that there are 4 different substituents around this guy and this guy, right? Same thing for this one. Here we have a 1, 2, 3, 4, 5 carbon sugar. How many chirality centers are present? There's 1, 2, 3. Okay, and that's the purpose of the Fischer projection, is to easily be able to see that. Okay. Now we draw it in this nice little 2-dimensional, like just square type complex. Okay. What is this trying to be representing when we try to take it back to bond line? Okay. So in the Fischer projection, what we imagine is that the vertical lines, I always get so confused, vertical lines are our dashes, right? So our dashes, and then the horizontal lines, if we go here, our horizontal lines are our wedges from the carbon. All right, so if I took this guy, let's say, and I drew it in attempts with our wedge and dash convention, I would have these guys on the dash. So this would be dash, 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 whereas these horizontal lines would be on the wedge. And so it's the same exact thing going through the entire molecule. The next carbon would be dash, 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 wedge, wedge, wedge. And so this is how we're drawing the Fischer projection. Okay, and so then that would end with a carbon, hydrogen, double bond, and this is CH2OH, et cetera, et cetera. We'll go ahead and finish it. Hydrogen, OH, hydrogen, OH. Do you catch my burps too in the videos, or?
I've been asked until you mentioned it.
Is that coffee? Okay, so this is the basics, okay? Again, though, I said, well, the reason why we do this is, first off, to easily see chirality centers, but second, it makes it really easy to see whether or not we have an enantiomer of a sugar versus a diastereomer, okay? So for example, if we had our Fischer projection for whatever this molecule is, right, and we imagine here's a mirror right down the middle, it's very easy to draw the enantiomer of that, right, compared to if we had it all in bond line and trying to draw the mirror image of it, right? So to draw a mirror image of this, all we have to do is imagine a mirror down the middle and just reflect it over here, okay? So these guys are enantiomers, whereas over here, it's easy to see the relationship between these two. They're not enantiomers now. What are they? They're diastereomers, okay? And again, that is the purpose of the Fischer projection. It's to easily see whether or not something is an enantiomer versus a diastereomer. Now, what's the problem with the Fischer projection? What if I said, okay, we're going to assign configuration about this carbon? What's the problem with that right now?
We don't know what R is.
We don't know what R is, so yeah, number one, we don't really know what those groups are, okay? But what if it was instead something like this, where we knew what the groups were? Right, and I said, okay, how many chirality centers are in this? We've got one, it's right here. What if I want to know if this is R or S? What's the problem with this? Okay, so as we know this right now, if we wanted to draw this in terms of bond line, we would have this guy like this guy like this. We could draw this guy out here, OH, right? Because this is what the Fischer projection looks like. We have those guys, or the vertical on the dash, the horizontal on the wedge. We could say this is CH2OH, and this is COH double bond, right? How are we used to drawing, or how are we used to imagining this molecule to actually assign configuration? What do we normally have to have? We have to have, or what we've been used to is two solid lines, right? One on the wedge and one on the dash, right? This is how we've learned how to assign configuration. How do I take this and make it that so that I could assign configuration? That's the question, right? So I think mentally maybe you could try to manipulate that, but there's a nice little trick that we're going to learn that allows you to take this guy into this guy so that you can assign configuration, okay? And so the first thing that you're going to do is you're going to come back to your original Fischer projection, and you're going to pick one horizontal line, okay? So what is a horizontal line? It's this way, right? Straight across. I'm going to pick one of these guys, this one, let's just say, okay? And we're going to draw a carbon. We're going to take one of those and we're going to turn it into a wedge. So we picked one, we're turning it into a wedge. That's OH. We're then going to pick one vertical and we're going to turn it into a dash. Okay, so I'm going to go ahead and take this one for my carbon, take this guy, and we're going to turn that into a dash. Dash, 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 CH2OH. The other two are going to remain solid lines. Okay, so then this guy up and this guy over, those remain solid lines. So we have an H, we have a C, OH, double bond. So now we're in our standard bond line structure. How do I assign configuration at this point? I've got two solid lines, I've got a dash and a wedge. If I wanted to assign R versus S, what do I need to do with my substituents off of this chirality center? I need to assign them priorities. So in our first little iteration of this, we've got a carbon. Who gets number one? Who is first priority? The carbon, the O, the carbon, or the hydrogen? The O. So this guy is going to get 1. Who gets 4? That's a nice easy one. So 4 is always going to be lightest, or least atomic mass, so that's hydrogen. Now who comes next? Who is, so this is 1. If this is 4, we'll erase that guy, make it 4. Who is 2?
It's going to be the top one.
Right, so we're comparing carbon versus carbon. We can't do anything. But now this carbon's attached to 3 oxygens, whereas this is attached to an oxygen, hydrogen, hydrogen. So this guy is going to be our 2. This is our 3. Now what do I need to do? Who has to be on the dash? 4. So what can I do to get that to the dash? I can switch these, right? So we'll go ahead. We've got carbon, dot, 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 dot. This is going to be 4. This will be 3. I've inverted the configuration. Now what do I have to do to get back to the original configuration?
Change the others.
I have to switch the others. So now this is 1. This is 2. How do I get from 1 to 2 to 3, ignoring 4 entirely? I go 1 to 2 to 3. Is that clockwise or counter? Clock. So what is clockwise? This is R. So again, the reason why we get 4 in the dash is because we want to ignore it. And getting from 1 to 2 to 3, which way do we have to go? This way or this way? Clockwise, so it's R. Same exact thing that we have been doing to assign configuration. What is the only thing that changed? Up here, we picked a horizontal line. Where did we put it? Horizontal was going to be on the wedge. We picked a vertical line. It was going to be on the dash. If I had picked this guy, same thing would have happened, right? You pick one horizontal, you pick one vertical. The other two stay solid lines. Doesn't matter which ones you pick, you'll get the same answer regardless. Yes?
Can you go over again how you went from the dashes to the...
Okay, so unfortunately, this got interrupted. So in these types of problems, we're taking a Fischer projection and we're trying to assign absolute configuration to the chirality centers or the chiral centers that are in each of these molecules that are being depicted right now in the Fischer projection, right? So we just talked about how to do that. So we have two different molecules here, and both of them differ in the number of chiral centers that are present. So in molecule A, we'll note that, again, for a chiral center, we need sp3 hybridized carbon, and we need 4 distinct groups attached to it, right? So for this guy, there's actually only one chiral center. It is this carbon. And again, with these Fischer projections, the vertices of these lines are essentially supposed to represent carbons. So this guy is a carbon, even though it's not drawn. And again, our 4 distinct groups are hydrogen. We've got this carboxylic acid group. We've got this amine. And then we've got this CH2OH, this alcohol group on the end. Okay, so these are 4 distinct, unique groups around this sp3 hybridized carbon. For molecule B, we'll go over here to B. We've got a couple of different chirality centers. So we've got 1, we've got 2, and we've got 3. And again, this is supposed to be the helpfulness with respect to Fischer projections. We can easily see that there are 4 different chirality centers in this. If we had drawn this in bond line, it may be a little bit more difficult to see, okay? All right, so we're going to start with A. And again, the purpose of this, we're trying to say from this guy, we go over here, we want to assign absolute configuration. And what we mean by that is we're trying to assign whether or not this is R versus S, okay? R versus S is going to tell us the absolute configuration about this chiral center, and that's the purpose of why it was designed. It tells you specifically in 3-dimensional shape, or 3-dimensional space, how each group is arranged around that chiral center, okay? All right, so now to do that, we've kind of talked about how these various lines represent different configurations, right? So in these Fischer projections, any type of horizontal line is supposed to be representing bonds that are coming out at us, right? So we can draw like a little bow tie here to represent this. And then vertical lines are supposed to be representing our dashes, right? And so we can draw a dashed bow tie. Carbon, carbon, okay? Now, with respect to trying to assign configuration, right, we're not used to looking at 2 bonds coming out at us and 2 bonds going into the board. That's very confusing for us. Instead, what we're used to looking at are 2 bonds that are in the same plane as the paper that we're dealing with or the board, 1 bond that's coming out at us, and 1 bond that's going behind into the board, right? So we're used to designing or assigning configuration given this convention, right? That's not really what they're telling us in Fischer convention. What they're telling us is, the horizontal lines are coming out at us and the vertical lines are going in. So how do we convert from Fischer to our nice little means by which we've been assigning configuration? So what we're going to do is we're going to pick 1 bond, right? So 1 bond that is horizontal, and we're going to make it a wedge, right? So again, we can pick either this guy or this guy. It does not matter, but we have to pick one of them, and we're going to make it a wedge, right? So I'm going to pick the right side, the carbon to nitrogen bond, and I'm going to make this a wedge. And then same thing for the vertical ones. We have to pick one of these guys and we have to make it a dash, right? So what I'm going to do, I'm going to go ahead and pick the top one and make it a dash. Okay, so now we have two lines that are in the plane. We've got this guy, and then we've got a wedge and we've got a dash. We should be able to utilize that to assign configuration, right? Now, I do want to stress that it did not matter who I picked. I will get the exact same configuration if I had instead assigned this bond, the wedge, and kept this the line, or I had assigned this bond, the dash, and kept this the line. It does not matter, right? You're going to get the same thing regardless, okay? So now what I'm going to do is I'm going to take this and I'm going to redraw it to have my carbon with my two solid lines, to have my wedge, and to have my dash, okay? I'm also going to start assigning priorities because that's the next step. Once we have this in our little two solid lines, wedge and dash form, we're going to assign priorities to the groups or the substituents around that chiral center, okay? So we assign priority via atomic mass, and we compare the things that are directly attached. We've got a carbon, hydrogen, carbon, nitrogen. So this guy, nitrogen, is the heaviest. It's going to be number 1. I also know that this guy is the lightest. It's going to be number 4. So we have number 1, we have number 4. And we can go ahead and put that on our little molecule here. So now the question is, we've got carbon attached to a oxygen, hydrogen, hydrogen. So this is an oxygen, hydrogen, hydrogen, versus a carbon that is attached to an oxygen, 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 right? So again, we're looking at first point of difference. This guy is oxygen, whereas this guy is hydrogen. So because of that, this will get number 2, and then this guy will get number 3. 2 and 3, okay? All right, so now we're going to rearrange everything so that 4 goes on the dash. So what I'm going to do is I'm going to go ahead and switch 2 and 4. So this will be 4 now, and this will be 2. I have inverted configuration. So to get back to the original configuration, if I switch these, then I also need to switch these. And again, if you want to rotate this and try to imagine this visually, you can. All I'm saying is I think it's easier just to switch, put 4 on the dash, but then I have to just switch the other 2. So this is going to be 1, and this is going to be 3. So now, how do I get from 1 to 2 to 3? Which direction do I go in? I'm just ignoring 4 entirely. I am going clockwise here. Clockwise. So this is R. And we can go back to this and say absolute configuration at this chiral center is R. Okay, so we'll move on to number B. There are 3 chirality centers in here, so I'm going to quickly go through these guys. Again, we're going to pick one of the horizontal lines. We're going to turn it into a wedge. We're going to pick a vertical line and turn it into a dash. And so I'm going to follow the same convention that I did over in A. So I'm going to start with this. We'll call this carbon 1. This is carbon 2. This is carbon 3. So for carbon 1, I'm going to leave hydrogen on the dash, or on the solid line. I'm going to leave the carboxylic acid on the solid line. I'm going to turn the OH into my wedge. And then, actually, I switched things, but it should be fine. I'm going to go down below with the dash. And that down below is just going to be a carbon, and we're just going to kind of leave it like that because, again, I just want to assign priorities at this point. All right, so we have carbon. The hydrogen is going to get 4. The OH is going to get 1. Now we're competing between this carbon and this carbon. This carbon is attached to an oxygen, a hydrogen, another carbon. This carbon is attached to an oxygen, oxygen, oxygen. So this would get 2, and then this guy would get 3. So again, I need to get 4 on the dash, so I'm going to switch their places. So this will be 3, this will be 4, but if I switch their places, I have to switch the other 2, so this becomes 1, and this becomes 2. So to get from 1 to 2 to 3, we're going to go in a clockwise direction, so this is going to be R. So we'll do the same thing for this guy. I'm going to pick the same ones. So we have wedge, and then we have dash. This is carbon 2. Now, for this guy, we've got the OH as 1. We'll have the hydrogen as 4. So now the OH is over here, 1 and 4. Now we have a carbon attached to an oxygen, hydrogen, carbon, or carbon attached to an oxygen, hydrogen, carbon. We can't figure out there. So we move up. This is a carbon attached to an oxygen, oxygen, oxygen. This is a carbon attached to hydrogen, hydrogen, oxygen. So this guy's going to get 2, and this guy's going to get 3. So again, we're going to switch things so that 4 is on the dash. So we have 4 down here. That means 3 is going to go to the wedge. Then I have 2 and 1. So we have 1 to 2 to 3. This is counter. So this is an S. And then finally, down here, we'll have a carbon. I'm going to keep the exact same one. So we'll have wedge dash. Hydrogen is 4. Oxygen is 1. Now we've got a carbon attached to a carbon, an oxygen, a hydrogen, or a carbon attached to a hydrogen, hydrogen, oxygen. So it'd be oxygen, carbon, hydrogen. It'd be oxygen, hydrogen, hydrogen. So this guy would get 2, and this guy would get 3. Again, we've got to switch things to get 4 on the dash. So these guys are going to switch, and then these guys are going to switch. So this is 4, this is 3, this is 1, this is 2. We have 1 to 2 to 3. This is clockwise. This is R. So R, F, R on that last one. And again, I go through these pretty quick because, ideally you would have gotten the whole assigning priorities down at the very beginning of this chapter and determining R and S with respect to absolute configuration. So I try to sail through these at the end. If you're still having problems with this, though, I would go back and I would utilize the textbook. There's a lot of resources available in Wiley Plus that are there available to use. It's in the actual Wiley Plus, right? If you don't have the textbook as on you, you can actually go through and do all the practice problems, etc. Via Wiley Plus. So that is not only the homework site, but it's also a site where you can access the textbook as well. So let me know if you guys have questions. Email me. And then, yeah, that's all I have for chapter 5. So this is it for this chapter.